Securing the low-altitude airspace around a massive installation like Travis Air Force Base is a chaotic, high-dimensional inference problem. To maintain awareness over that area, the system must simultaneously ingest raw physical measurements from up to 12 4D radars and 12 electro-optical and infrared cameras. But those measurements are rarely clean. Actual targets are obscured by weather patterns, ground clutter, false tracks, and constant network latency. Deterministic point tracking from a single sensor mathematically fails under these conditions. Extracting a true object requires probabilistic multimodal fusion. This schematic details the proposed physical AI architecture, the Predictive Tensor Control Plane, or PTCP, paired with Tensor Network Quantum Gravity, or TNQG. Looking at the center nodes, raw telemetry flows directly from edge AI preprocessing into the multi-sensor fusion core. The physical installation operates as a distributed sensory motor system. Radars and cameras act as the perceptual field. Edge nodes provide local reflexes, and algorithms govern memory. Human operators no longer need to parse raw radar returns. They make decisions based on synthesized cross-domain anomaly scores. The first computational step occurs physically near the radar clusters. Here, a software module called the Sensor Edge Polymorph parses specific vendor data directly from the software development kits. These disparate feeds are mapped into a unified state vector. This single coordinate combines object kinematics, camera orientation, and local network health into one continuous mathematical space. Aligning this vector accurately requires strict geodetic calibration of every sensor, alongside exact GPS-disciplined time synchronization to correct for latency. If you remove precise coordinates and synchronized timestamps, multi-sensor fusion is impossible. The architecture degrades into mere data aggregation. To establish a baseline, the PTCP slow path uses kernel density estimation, fitting historical telemetry into a probability density surface. Calculating this joint probability tensor creates a computational bottleneck. Tensor train decomposition solves this, factorizing the massive space into a linear chain of lower dimensional cores. An operational fastpath then queries this compressed tensor core in real time, instantly assigning an anomaly score to incoming sensor data. By compressing the baseline, an intractable big data calculation is reduced to a low-latency query. The Tensor Network Quantum Gravity framework serves purely as an operational geometry engine. It makes no claims about physical cosmology. It maps the physical network, radars, cameras, and incoming tracks as a dynamic mathematical graph. This introduces emergent distance. Two physical nodes might be inches apart, but if signal uncertainty or measurement covariance rises, their emergent distance increases. The algorithm calculates minimal cuts across this flexible graph to locate the weakest information links. It then autonomously triggers the most efficient physical action, like slewing an infrared camera precisely to an uncertain radar track. Treating data links as operational geometry allows the system to prioritize attention and collapse uncertainty before a human ever intervenes. When a multi-track drone swarm penetrates an installation perimeter, the math is applied to a high-stakes scenario. The system ignores individual radar blips. Instead, it evaluates the spatial coherence of the swarm as a single group against the learned pattern of life baseline. This schematic details the back projection process. The algorithm traces track history backward, merging it with context to estimate launch origin. The red concentric rings represent the origin posterior surface, accounting for variables like wind and unknown hardware performance. Outputting a broad probability region, rather than assigning a deterministic single point, is the only scientifically valid method for origin inference. This exact rigor governs unidentified anomalous phenomena. The system operates on strict rules of epistemic humility. This diagram outlines the required output schema. An event is classified as an anomaly only with absolute multi-sensor coincidence and comprehensive calibration metadata. If supporting evidence is missing, the decision layer explicitly throws an abstention flag. Programming an AI to declare an event as unknown prevents unsupported claims and maintains the integrity of the investigation. This diagram visualizes the controlled polymorphic architecture. The identical algorithmic core operates in 6 distinct deployment roles. Moving from ED ingestion on the left to the forensic digital twin on the right, the core adapts strictly based on required latency budgets. By utilizing a unified, configuration-managed core, The system guarantees every real-time alert and forensic reconstruction is exactly identical, fully auditable, and scientifically defensible.